titled Thermodynamics Still Very Basic, right? So, still very basic. Now the first problem of the sheet is about a relationship that connects the internal energy, the pressure and volume of an ideal gas in an adiabatic process. A very hypothetical situation, nevertheless. A plus B PV. A and B are constants, P pressure, V volume, U internal energy. We want to find the ratio of the molar specific heats of the gas, that is Cp by Cv, that is gamma is what we seek to find here. Now, realize that this could be written as A plus B, PV is nRT, right? That's U. Now du, change in U, d of A will be 0, that's going to be BNR dt. Yes or no? du is change in internal energy, which is going to be NCV dt, which is going to be NCV dt. So this could also be written as NCV dt, which gives us direct access to CV. CV then, as you can see, is B, isn't it? See, BR is CV. CP is R more than CV. R more than CV, that's CP. Adding R to CV, and gamma therefore, which is CP by CV, is B plus 1 is to B. That's gamma. C B plus 1 is to B. Right? Where have I taken A as 0? No, but for a special case, t equal to 0, u is 0. So at t equal to, no, see, please understand, u is not, u is, in a situation, u is not absolute, right? This is a case in which we have defined u like this. Otherwise, we define only change in u, which is NCV into dt. Or if nothing is given, then we take u as NCV into T, if nothing is given, right? But otherwise, U is like internal energy, you know, we can define its reference also, because we are more interested in change in U, right? All right. Can I wipe this off? Problem 2. Volume is given as, in a certain process, P by T to the power 0.33, where K is a constant and there is a certain process in which this happens. We want to figure out the nature of this process. We want to be able to figure out the nature of this process, right? Now, realize that this can be written as P by T is what? NR by V? P by T is NR by V? Yes or no? That's V. P by T is NR by V. And this gives me V to power 1.33 cross multiplying equals K into NR to the power 0.33, which is a constant, which means V must be constant for the process. Therefore, the process must be an isochoric process, constant volume process. All's good? Number 3. Two different ideal diatomic gases A and B are initially in the same state. Two different ideal gases A and B are initially in the same state, right? Same state means what? Same thermodynamic state means the same pressure volume and therefore the same temperature, assuming the same number of moles, but in any case the same pressure and volume. We'll also assume the same temperature, right? Now, A and B are then expanded to the same final volume. They are in this state of pressure. They are initially in the same, this state, initial pressure, initial volume. Both gases are at this point in the PV diagram, right? They are expanded through adiabatic and isothermal processes. A, adiabatically, B, isothermally. Like I've said before, adiabatics will fall faster than isothermals. So, if this is adiabatic, which is for A, then this would be a more gradual process, which is isothermal for B. So that their final volumes are the same. Right? A undergoes an adiabatic expansion, B undergoes an isothermal expansion, so that they arrive at the same final volume. Right? Okay. If PA, okay, let's say the pressure here is PA, temperature is TA, the pressure here is PB, temperature is TB. Very simple now. From the figure itself you can say that PB more than PA, PB is more than PA. That's readily observable. Also realize that this point and this point, this point and this point are at the same volume, and this is higher pressure compared to this. So this would be higher temperature compared to this. Therefore, TB will be higher than TA. Yes or no? If pressure here is higher than this and the same volume, so the temperature here would be higher than the temperature there. TB will be more than TA. Clear? Right? Shall we move? Number 4. One mole of a gas is subject to two processes AB and BC. So the indicator diagram, 1 mole of a gas subject to an AB and a BC. AB is an isobaric process. And BC is a polytropic process. BC is a polytropic process given by PV to power n equal to constant. PV to power n equal to constant, that's BC. We can conclude if T is the temperature, W is the work done by the gas, V is the volume, U is the internal energy, as is customary. Now, this volume is the same V naught. This is 2 V naught. This is 3 V naught. Right? Now, when I go from A to B at constant pressure, if I increase the volume, if at constant pressure, if I increase the volume, what happens to temperature? Increases. So if the temperature is TA here and the temperature is TB here, then TA will be smaller than TB. Temperature has increased. Yes or no? Right? Now, obviously, you know, VA is less than VB, all that is obvious. Now, area under this, see, both these have the same width, V naught. But this has smaller and smaller ordinates. Okay. Therefore, this area is more than this area, dotted area. The shaded area is more than the dotted area. So, the work done in AB is very clearly more than the work done in BC. Work done in AB is more than the work done in BC. So, C is wrong. PB less than PC? Nonsense. TA equal to TB equal to TC? Stupid. So if TA less than TB, if temperature at A is less than temperature at B, then we can simply say internal energy at A is less than internal energy at B. So option D seems correct. Option D seems correct because TA less than TB, the internal energy at A would be smaller than internal energy at B. Right? Now, number 5. For a thermodynamic system, the pressure, volume and temperature, let's say, is given as alpha T squared by V. Alpha T squared by V. P is the pressure, T is the temperature, V is the volume, alpha is a constant. The work done by the system in a constant pressure process, in a constant, that means the process is actually alpha T squared by V equal to constant. That's it, because P remains constant, right? So alpha T squared by V equal to a constant is the nature of the process. We want to find the work done in the process when temperature changes from T naught to 2T naught. Temperature changes from T naught to 2T naught. We want to be able to calculate the work done. We want to be able to calculate.
If I say PV is alpha T square, there's nothing wrong with this. PV is alpha T square. And it is an ideal gas, so we can say that PV is nRT and T will come out to be a constant.
PV is nRT. Yes, PV is nRT is alpha T squared. Right, so T is constant for the process. So it's how can T vary, right? So there must be a misprint in the problem. There must be a misprint in the problem. You're right. You're right. The pressure, volume, and temperature go as P is alpha T squared by V, where alpha. So now the way I will interpret this is that in this, they are assuming that PV equal to nRT is not holding good. We will assume that the gas changes are not commensurate with PV equal to nRT. This is what we'll assume. You know, there is a departure from ideal gas behavior. There is departure from ideal gas behavior is how we will assume this to be. Huh? No, no. In a polytropic process, PV equal to nRT is still holding good. In addition, PV to power X is constant. I never said in a polytropic process it's not an ideal gas. It's still an ideal gas, but this one, very clearly, since the temperature is varying, even though from ideal gas conditions it must remain constant, we will assume that, you know, the gas is not sustaining ideal conditions. PV equal to nRT is not holding good. Instead, PV equal to alpha T squared is the departure from ideal gas behavior. Right? We will assume that. Now, PV is alpha T squared. Right? PV is alpha T squared. So, D of PV is 2 alpha T dt? Is 2 alpha T dt? Yes or no? So, PdV plus VdP is 2 alpha T dt? It's a constant pressure process. So dP must be 0. So this goes into oblivion. Right? So work done, which is P dV, is the same as 2 alpha T dt. Right? So the total amount of work done would be sum of all the dWs, which is 2 alpha T dt. T runs from T naught to 2 T naught. Yes or no? 2T when integrated will give me T squared. So this is alpha into 4T squared minus T squared. That is 3 T naught squared. That's the work done. Right? Yes or no? Can I wipe this off? Although, very honestly speaking, you know, if it's a process specific equation, under normal circumstances, PV equal to nRT holds good even in a process specific equation. In a process specific thermodynamic equation, see dq is du plus dw is first law of thermodynamics. But in a process specific scenario, dq could be 2 dw plus 3 du. You know what I'm saying? Heat supplied is work done plus change in internal energy. That's universal and cardinal. But in addition to this, if someone talks about a certain process, then in that process one could have also said 2 dq is 3 dw plus 5 du. Could be in addition to this condition could also hold good, which would give me, see, PV equal to nRT is cardinal, right? But PV to power R equal to constant is in addition to PV equal to nRT. So this is cardinal. Similarly, this is cardinal. In addition, this could also hold good. This could also hold good. All right. So in which case, you know, if somebody says there is an ideal gas doing this, there is an ideal gas doing this, find its pressure volume variation or find the equation of the process. What you would do is, let's say if I eliminate dq, 2 dw plus 2 du, for example. Now if I plug in 2 dw, so this gives me like a 2 dw plus 2 du is 3 dw plus 5 du, for example, right? It gives me this. Yes or no? This gives me like dw equal to minus 3 du, right? This would give me, say, pdv. Pdv is minus 3, right? Work done for a small change in volume dv would be given by pdv, right? Equal to minus 3 dv. Let's say for 1 mole of the gas, say 1 mole of the gas was involved, du is going to be cv dt. Yes or no? Now, in this I can write as P as nRT by V. Say for 1 mole, RT by V. This will give me RT by V. And now I can separate variables. So R dV by V, R dV by V is minus 3 CV dt by t. And now I can integrate log etc., and I would get a process specific equation. It doesn't mean that PV equal to nRT is not good. It still means that in addition to PV equal to nRT, the process entails this condition. That means if I write it as R log V plus 3CV log T equal to constant. On integrating both sides, bringing it here and integrating, there is going to be a constant of integration that's going to emerge, right? Which would mean log of V to power R T to power 3CV equal to constant. This is what it would mean. If log of this is constant, this would mean V to power R T to power 3CV is constant for the process. That's a very process specific condition. It doesn't mean that PV equal to nRT is not good. So under normal circumstances, when they give you something which is very process specific, if nothing is said, you would still assume PV equal to nRT. This one last problem that we did was in a certain sense faulty. In a certain sense, I would say was faulty. But since there was a discrepancy, we assumed that PV equal to nRT was not good because it very clearly said that there is change of temperature. Right? So we will assume that in that case, but in general, if nothing is given, we will at all times assume that the first law of thermodynamics is good in addition to, let's say, a process specific condition. PV equal to nRT holds good in addition to, again, a process specific condition connecting pressure and volume. In a polytropic process, PV to power x equal to constant, it means that PV to power x is constant, but PV equal to nRT is also true. In an adiabatic process, PV to power gamma is constant. Doesn't mean that for that process PV equal to nRT is untrue. PV equal to nRT is also true, right? So just in a very general sense, let me fix things here. Shall we proceed to the next problem? Number 6. A vertical cylinder of CSA. CSA means cross-sectional area. A, right? This is a vertical cylinder and it has cross-sectional area A. CSA means cross-sectional area A. There is atmospheric pressure P0 and there is mg, the weight of the piston, and there is an ideal monoatomic gas inside this. For a monoatomic gas, what is CV? 3R by 2, right? And there is a heater. There is a heater that supplies heat at the rate of Q joules per second. This supplies heat at the rate of Q joules per second. Q joules per second is the rate at which this supplies heat. Now, it is known, we will also assume that the heat that this is supplying, does not get dissipated through the walls. So that way, these walls we will assume are adiabatic. These walls we assume are adiabatic, will not exchange heat with the surroundings. There is an external heater which is plunged into the gas, which is supplying heat at the rate of Q joules per second, but nothing through the walls of the container or the cylinder, right? Now, it is given that the pressure of the gas remains constant. Pressure of the gas remains constant. The velocity with which the piston moves upward under the condition that the pressure of the gas is constant, assuming no heat transfer through the walls of the container. Now, if the pressure of the gas is constant, then what was the original pressure? See, the piston was originally in equilibrium. This piston was feeling pressure plus mg by A. Was the, right? And in equilibrium, the pressure of the gas must have just balanced P0 plus mg by A. Right? So pressure of the gas remains constant and is equal to, takes care of pressure because of atmosphere plus pressure because of the weight of the piston. plus pressure because of the weight of the piston is managed by the pressure of the gas, which remains constant. Clear? Now, see a certain intermediate state of this piston. This is a certain intermediate state of the piston. And say it is at a distance x from the bottom. It's at a distance x from the bottom. And it is moving up with a velocity v. It is moving up with a velocity v. The volume here of the gas then would be A into x. Right? And it is receiving heat at the rate of q joules per second. It is receiving heat at the rate of q joules per second. We then want to find the velocity of the piston. We then want to be able to find the velocity of the piston. Now, first things first. First law of thermodynamics, pressure of the gas remains the same. Say Pg, which is this pressure of the gas, P naught plus mg by A. Now, say in a small time dt, what would be the heat supplied? Q dt? In a small time dt, the heat supplied is going to be Q dt. Yes or no? Now, where does it go? Change in internal energy plus work done. There is volume expansion and consequently work done. Right? Work done will be pressure of the gas into a small change in volume. Let's say in a small time dt, this moves up by a small amount dx. So the work done by the gas would be pressure of the gas into change in volume. Change in volume is going to be what? A into dx is the change in volume then? Yes or no? Plus change in internal energy. Change in internal energy would be, let's say, the change in temperature in that small time is d capital T, right? So this is going to be how many moles? Okay, does not matter. N Cv. Cv is 3R by 2, monoatomic gas, right? 3R by 2 into dt. dt is the, d capital T is the change in temperature in this. Oh, 1 mole is given? Okay. Okay. Yes or no? Now, realize that for the process, pressure of the gas into volume. Volume here is A into x. Volume is A into x. And let's say the temperature here was T originally, right? At some instant of time it was capital T. Then pressure into volume is 1 mole N1 R into capital T. Yes or no? So can I say that R dt is going to be pressure of the gas into A into dx? Can I say this? Can I say this? So this R dt that appears here, could be written as pressure of the gas into A into dx, right? Pressure of the gas into A into dx, and this R dt is pressure of the gas into A into dx. Yes or no? Does it make sense? Does it make sense? Right? Now, which means Q dt, the heat supplied, this would be 5 by 2 pressure of the gas into A into dx. What's the velocity? Dx dt is going to be the velocity. Pressure of the gas is like same as Pg. So dx dt would give me the velocity. which is 2 by 5 Q divided by pressure of the gas. Right? And pressure of the gas you can replace by which remains constant as P naught plus mg by A. Is that all right? You have a question, Raj? No? Okay. Shall we proceed then? Yeah, you have a question. You have a question, no? You got it? dx dt brought here. So 2q by 5 P of the gas. 2q by 5 P of the gas. P of the gas is P naught plus mg by A, which remains constant. All's good? Number 7. A certain amount of a diatomic gas undergoes a polytropic process. Say, assume that the polytropic process is PV to power x equal to constant is the polytropic process. Assume that it undergoes this process, right? In which it absorbs 100 joules of heat. 100 joules of heat is absorbed and performs 25 joules of work. Performs 25 joules of work, right? We want to be able to obtain the equation of the process. That means we want to be able to obtain the value of x. That's all that we want to do here, right? Now, okay, tell me what would be delta U, change in internal energy in this case? 75 joules, first law of thermodynamics. Right? Now, in a polytropic process, work done is what? NR delta T by 1 minus x, isn't it? NR delta T by 1 minus x is the work done in a polytropic process where delta T is the change in temperature, final temperature minus initial temperature, right? And that's given to be 25 joules. That's given to be 25 joules. Delta U would be NCV into delta T. NCV. For a diatomic gas, CV is 5R by 2. CV is 5R by 2 into delta T. That's given to be 75 joules. Yes or no? Now, what is my objective? My objective is to be able to compute x. I divide, say, this by this. If I divide this by this, I get 5 into 1 minus x by 2 equal to 3. This by this, isn't it? NR delta T would get cancelled. Bless you. So this gives me x equal to minus 1 by 5. 5 minus 6 minus 1 by 5. X is minus 1 by 5. Yes or no? Yeah, I have a question, no? No? X turns out to be minus 1 by 5. So the equation of the process is going to be PV to power minus 1 by 5 equal to constant. That's the equation of the process, polytropic process. Yes, your attention please then. So CV of a gas is given to be 3 plus 2T. T is the absolute temperature of the gas. Then the equation of the adiabatic process for such a gas. Equation of adiabatic process for such a gas is what we need to find out. Right? Now, in an adiabatic process, dq, which is du plus dw, that must be 0. That's true for an adiabatic process, right? du, that small change in internal energy, let's say assume 1 mole of the gas, would be Cv into dt, right? Work done is going to be Pdt, Pdv for a small change in volume, that must be 0. That's process specific. Now, P for 1 mole can be written as RT by V. P for 1 mole could be written as RT by V. And this Cv could be written as 3 plus 2T dt. And if I divide by T, then I can bring this T below, plus RdV by V must be 0. How about it? Right? Now, when I integrate, 3 by T would give me 3 log T. 2T by T is 2. When I integrate, I get 2T. This is R log V. That must be constant. Right? Now, let me simplify this a little bit. See, any number A can be written as log of e power A, isn't it? Log of e power A. So this 2t I can write as log of e power 2t, yes or no? So that I have all three logarithms, right? So this would give me log of t cubed into e power 2t into v to power r equal to constant. This is what I get, which means this must be constant. So the equation for the process is going to be t cubed e power 2t, v to power r is constant. Yes or no? That's process specific. I hope all of you could figure out whatever I have done here in the algebra. So we have a cylindrical tube of uniform cross-sectional area A fitted with two airtight frictionless pistons. This is one piston, this is another piston. Initially, the pressure of the gas in this is P naught and temperature is T naught. Atmospheric pressure is also P naught. So this P naught A and this P naught A will maintain equilibrium of this piston, this P naught A and this P naught A will maintain equilibrium of this piston, right? Now, so then if there was a string that was just joined at this instant of time, it will have no responsibility to maintain equilibrium, so there would be no force in the string initially. It has no role to play. It is just connected, just barely connected, right? Now, the temperature of the gas is increased to 2T naught. The string AB is inextensible, so it will prevent motion of the pistons. So the volume will remain constant of this region. The volume will remain constant because if the volume would have changed only if the string conceded. The string cannot concede, right? So since the string remains constant in length, inextensible, this volume is not going to change. So whatever happens here is at constant volume. At constant volume, if you double the temperature, what happens to the pressure? It will get doubled. So the pressure will become 2P naught. That's a new state. Now, let me look at the free body diagram of one of the pistons, for example. Let me look at this piston connected at B, right? If I look at the free body diagram of this piston, it's in equilibrium, right? It's in equilibrium. Because of atmosphere, there is P naught A acting like this, right? The new pressure is 2p naught. So there is 2p naught acting like this, 2p naught A acting like this, right? That means there is a net force because of the pressure P naught A acting to the right, and to maintain equilibrium, therefore, the tension in the string must be P naught A leftwards, so that equilibrium of the piston could be restored. Do you all understand this? So the tension in the string must be P naught A, so as to counter this difference to P naught A minus P naught A. To counter that difference, this must take place. All right? Do you need help in 10, 11 and 12? Anyone? Because I thought they're very straightforward. No, I will have to calculate. You can, one of you who solved the whole thing can give me the answers instead. It's direct formula, isn't it? So if you still want, I'll do the calculation for you. But okay, is there anyone who solved 10, 11, 12? 10, C, A and D, Delhi, CAD. CAD is the answer. That's what you got? Right. Okay. So I'm not solving 10, 11, 12, right? Very straightforward problems. Okay. Let me look at 13 then. Let me look at 13. But so far so good, right? Not a problem. Are you all okay with this? Now number 13. So we have a horizontal piston cylinder arrangement. This is a piston. There is a heater which is supplying heat at a certain rate, and there is a mass M, which is how much? Which is 1 kg. And there is helium gas here, 8 grams of helium gas. 8 grams of helium gas here initially. And there is a light smooth adiabatic piston. This is a light smooth adiabatic piston, and there is a spring of force constant K equal to 300 Newton per meter. And the coefficient of friction is mu equal to 0.3 is the coefficient of friction. Here, between this and this. Not between the piston and the ground, not between the piston and the ground, but between this and the ground, the mass and the ground, which is outside the cylinder, say. Area of cross section of the piston is given to be 25 centimeters squared, which is 25 into 10 to the power 4 meters squared. Initially the spring is relaxed. The spring is initially relaxed, and the initial temperature T1 is given to be 400 Kelvin. The gas is slowly heated for a while so as to make the block just move. We want to find the work done by the gas. We will assume that the piston moves very, very slowly to the right. So that it does not develop kinetic energy. And all the work that is done is the work against atmospheric pressure, and the rest goes towards storing spring energy, elastic potential energy in the spring, right? Now, first of all, let us see what it takes to cause this to move. Compression in the spring. So that the spring force Kx naught will overcome mu mg, right? That's what it takes to move the mass m, right? So how much of compression of the spring is required to move the mass m? X naught units, such that Kx naught must just balance mu capital Mg, right? So this X naught can be computed mu mg by K. The X naught can be computed mu mg by K, whatever it turns out to be. 0.01 meters, right? Okay, 0.1 meters. Okay, that's what it takes to move the block. Just about move the block. Now, so which means now, as far as the cylinder is concerned, piston is concerned, let's say after a while, the piston has moved from this state, which is the initial state, to a certain intermediate state by an amount x. Now, what are the forces acting on the piston? There is kx, and there is atmospheric pressure, which is P naught A. Right? Yes or no? Now, essentially the piston moves to the right. We will assume that the motion of the piston to the right is quasi-static, essentially in equilibrium from instant to instant. Right? So at this instant, when the piston is here, the pressure in the gas, let's say, is P, an intermediate pressure P. Then this intermediate pressure P is computed using the following considerations. P takes care of P naught, pressure because of the atmosphere, plus pressure because of the spring force, which is Kx by A. That's the intermediate pressure in the gas. Right? That's the intermediate pressure in the gas. Now, I want to be able to compute the work done by the gas. I want to be able to compute the work done by the gas. While x runs from 0 to x naught. While x runs from 0 to x naught, the required extent of compression in the spring causing the mass to just about move. Right? So, at this stage, let's say, the pressure in the gas is P naught plus Kx by A. It's a variable pressure. That's the pressure in the gas. Right? Now, when the piston moves by a small amount, dx to the right, then the change in volume is going to be A into dx. That's the pressure in the gas. When the cylinder has moved by an amount x to the right, that's the pressure in the gas. Yes or no? Right? And when the piston moves by an additional amount dx to the right, pressure remains practically this. Change in volume would be A into dx. Yes or no? Change in volume of the gas chamber is going to be A into dx. So that's the work done by the gas. That's the work done by the gas. Yes or no? The total work done by the gas up to the required stage would be sum of all of this. That's going to be the work done by the gas, where x runs from 0 to x naught that we have already computed. Right? Which then reduces to pressure into P naught into Ax naught x naught plus half K A x naught squared K x naught squared. Yes or no? If I integrate this, I'll get x squared by 2. And A will get cancelled. So half K x naught squared. When I supply the limits, this is what I get. This is the work done. Right? So this could be looked upon as, this is the work done against atmospheric pressure. And this is the work done against the spring force, half Kx naught squared, which goes towards storing elastic potential energy in the spring, right? So this is the work done. X naught being computed, I can calculate the total amount of work done by the gas up to such an instant of time. Clear? Right? So that's part 1 of the problem. The work done. I'm not doing the computations here. We want to next find the final temperature, the heat supplied by the heater. Okay. Now, can I remove the clutter from here? We know x naught. Everything is known here. Can I remove this portion? This. Now, say the initial pressure is P naught. Initial pressure is P naught. when we just started to supply heat, and at that instant, say the volume was V0. And say the temperature was T1, say, at that instant, which was given to be 400 Kelvin, right? Now, pressure finally would be what? Pressure when it reaches the spring reaches a state of compression would be the pressure of the gas would take care of atmospheric pressure P0 plus pressure because of the spring, which is Kx0 by A. So the final pressure is going to be P0 plus Kx0 by A. That's going to be the final pressure. Yes or no? The final volume is going to be V0 plus Ax0. X0 is the amount by which the piston has moved to the right. So that's a change in volume produced. That's the final volume. And say the final temperature is T2. P0 we know. 1.013 into 10 to the power 5 Newton per meter squared atmospheric pressure. Or you can almost take it for an approximation sake, 10 to the power 5 Newton per meter squared. That's a good enough value. N, number of moles, is given to be 2, right? 8 by 4, mass by molecular weight. 2 moles of the gas, right? So now, can I say from this, P0 V0, P0 V0 by, or rather just P0 V0 must be equal to, P0 V0 by T1 must be equal to P0 plus Kx0 by A into volume V0 plus Ax0 by T2 must be equal to number of moles, 2 moles into R for 8 grams, 2 moles of helium, right? NR, isn't it? Can I say all of this? Initial pressure volume must be NR T1, final pressure, final volume must be NR T2, right? Can I say this? Now, very clearly, this gives me an opportunity to calculate V0. This gives me an opportunity to calculate V0 because P0 is known, 1 atmosphere, 10 to the power 5. T1 is 400 Kelvin. This right hand side is known to me, so I know V0, which I can plug into this. That V0 I can plug into this. X0 is known to me, P0 is known to me, right? So I can calculate T2 from these considerations. See, from these two, I can calculate V0 because P0 and T0. So that V0 which I have computed from these two, I can plug into this, right? And then from this, these two, I can calculate T2. The final temperature then could be calculated by plugging in the value of V0 because everything else is known here. So the final temperature could be computed from these two. So T1 known, T2 known. So change in internal energy can be calculated. Change in internal energy would be number of moles, which is 2, CV into T2 minus T1. Monoatomic gas, so CV is going to be 3R by 2. So I can calculate change in internal energy. I've calculated work done already. So what would be the heat supplied? Change in internal energy plus work done. Change in internal energy plus work done is going to be the heat supplied. Yes or no? Right? Let's look at number 14. All's good? Can I wipe this off? See, I have not done these calculations, but you should be doing these calculations. I don't do these calculations because I'm not going to appear for an exam. So, you know, I don't need to bother too much about it. But you guys should not behave like me. Okay? You should take every problem to its natural conclusion with numbers intact. Alright? So, you should do the calculations and avoid using your calcs. 2 into 8, weight. Approximately 15.999999 recurring. Don't fall in that trap. Okay, so you should do the calculations. Okay, let's look at problem number 14 then. Number 14. So here we have a frictionless piston dividing this cylinder into two equal parts. This is a piston that divides this cylinder into two equal parts, volume V0, V0. Bless you. I'm tempted to say something which would have been very inappropriate for the sake of this class. But don't push me to the corner where I become extremely verbose, vocal, and extravagant with things that I know. All right? Only thing is, I have to, reason I'm exercising restraint is because, right? Else you would have borne the brunt of this. Saurav, I will make sure that your huh? No, I know that. A poor fellow, I was trying to give him consolation. Offer him unconditional support against the attacks of the likes of. Okay, so this frictionless piston of mass m of the piston, dividing the cylinder into two equal parts, volume V0, V0, and length L, this spring is of natural length L. So is in of force constant K and of natural length L is in a relaxed state initially. Now, let's say the pressure was P0 and P0 initially in both chambers. Pressure was P0 and P0 in both chambers. And the temperature was T0. Initially, that was the initial state. Find the frequency of small oscillation of the piston given that the temperature is T0. Now what I'm doing is, I'm taking this is a position of equilibrium for the piston, isn't it? No spring force, P0 into A, taking care of P0 into A, net force on the piston is 0, right? However, if I shift the piston slightly to the right, there would be spring force. And now there is going to be difference in volumes in the two chambers. There would be force because of the difference in pressures in the two chambers. And there is a net force arising out, a differential of spring force and difference in pressures, etc., right? We first want to be able to establish that the force arising out of this displacement to the right would be a force to the left directed towards this equilibrium position and proportional to how far the piston is moved from the equilibrium position, causing us to believe that the motion of the piston is simple harmonic. That's the whole thing. Yes or no? Which means now I carry out the following. This was the position of equilibrium of the piston. Equilibrium position of the piston, right? And the piston is moved x units to the right. Piston is moved x units to the right. X units to the right. So which means now this chamber has a length L plus X, this chamber has a length L minus X. Right? So far so good, right? Now, if this be the case, and everything has happened isothermally, that means the temperature has been maintained constant, T naught, T naught. Let me first find out the pressure that results here, P1 and P2 here. Let me first find out the pressures resulting in this situation. Between this state and this state, I can apply PV equal to constant for this portion. Between this state and this state, I can apply PV equal to constant, right? So in either case, P naught V naught, P naught V naught is between these two is P1 into V1. That is P1 into V1 is what? L plus X into area of cross section. P1 V1 is the area of cross section of this unit. And the P naught V naught here is P2 into L minus X. Yes or no? Right? Suppose there were n moles of the gas involved. Suppose there were n moles of the gas involved in the process. Then each of these chambers had the same number of moles because same gas, same, 1 mole each. So this must be PV naught. PV must be R T naught. R T naught is maintained constant. Yes or no? P naught V naught must be R T naught. Right? Which gives us access to P1 and P2. Which gives us access to P1 and P2. So what are P1 and P2 then? P1, the pressure in the left chamber when the piston is moved x units to the right is going to be RT naught divided by A into L plus X. Right? RT naught by A into L plus X. Right? P2 is going to be what? RT naught by A into L minus X. These are the pressures in this intermediate state of displacement of the piston. Now let me look at the free body diagram of the piston. I want to show that the net force acting on the piston is leftwards, directed towards this equilibrium position, therefore restoring in character and proportional to x. If I can establish that, I will assume that x is small compared to L. I will assume that the displacement x is small compared to L because it's given that for small oscillations. That means x is small compared to other dimensions associated with the problem. So x small compared to L, eventually if required, we'll use that. Now, let me look at the free body diagram of this piston in this state, where the pressure in the left chamber is P1, pressure in the right chamber is P2. Very clearly, P2 is more than P1, as you can see, because the denominator is smaller. So there is P2 minus P1 into A acting to the left. There is P2 minus P1 into A acting to the left, yes or no? Also, there is spring force. Spring has got elongated by an amount x. So there is spring force Kx acting to the left. Right? So the net force acting to the left is going to be Kx plus P2 minus P1 into A. Right? Now let's look at that. For the piston then, the free body diagram, there is spring force Kx leftwards. There is spring force Kx leftwards. And then there is P1A to the right because of the left chamber. And P2A to the left because of the right chamber. Right? When it has got displaced by an amount x from the equilibrium position. So the restoring force is Kx plus P2 minus P1 into A. Right? That's a restoring force. That's a restoring force. Right? Let me simplify this. Can I remove the clutter from here? So F restoring is Kx plus P2 minus P1, which is RT naught. A will get cancelled. 1 by L minus X minus 1 by L plus X. Right? P2 minus P1 into A will give me this. Right? Which is Kx plus RT naught into 2L divided by L squared minus X squared 2x divided by this, yes or no? L squared now x is small compared to L, so L squared minus X squared is approximately L squared only, could be looked upon as approximately L squared because x naught squared, X squared is small, so ignoring this, right? That's a net restoring force, right? Which is K plus 2RT naught by L squared into X, 2RT naught by L squared into X. So the restoring force proportional to displacement from the mean position, equilibrium position, directed towards the equilibrium position and therefore restoring. This must be the equivalent force constant of the motion. This must be the equivalent force constant for the oscillator. K equivalent for the oscillator is K of the spring plus 2RT naught by L square. So the angular frequency for the oscillator is going to be what? Root K of the oscillator divided by the mass of the piston, which is the oscillator. So omega is known. So omega is also 2 pi times the frequency F. Omega is 2 pi times the frequency F. So F would be omega by 2 pi. This by 2 pi would give me the frequency of oscillation of the oscillator. Yes or no? Right? All's good? The molar specific heat of a certain process. The molar specific heat of a certain process is given to be Cv plus alpha V. V is the volume, alpha is a positive constant or just a constant. We want to find the equation of the process. Now, let me take 1 mole of the gas undergoing this process. 1 mole of the gas undergoing this process. Now, let's say if the change in temperature is dT, d capital T for 1 mole, then what would be the heat supplied? C into dt would be the heat supplied for 1 mole. That's going to be the heat supplied, which must be Cv into dt plus alpha V dt. Right? Now Cv into dt is actually change in internal energy. This is du. And therefore, from first law of thermodynamics, this must be dW, the work done. This therefore must be the work done. Right? Which means the work done, which we know is PdV for a small change in volume at a given pressure P. The work done is PdV. That must be alpha V dt. That's the governing equation. That's the governing equation which would eventually lead us to our destination of finding the equation of the process. Right? So far so good. Can I remove all of this? Now, P I can write as RT by V because I want to connect V and T, say. P I can write as RT by V. Alpha V dt, and I now want to separate the variables. So I get R by V dV, R by V dV minus alpha R by V squared, R by V squared dV, R by V squared dV minus alpha by T dt is 0. This is what happens. Yes or no? Hmm? When I integrate, I get minus r by v here. Minus r by v minus alpha log t equal to a constant is what I get. Constant of integration. So minus of this is a constant, so this must also be a constant. So which means this plus this must also be a constant, right? And now just to make things look commensurate, I can write r by v as e log of e to power r by v, right? Plus log of t to power alpha equal to constant. So this would give me log of e to power r by v into t to power alpha equal to constant, which means this must be constant, that means e to power r by v into t to power alpha must be constant. That's the equation of this process. You got the same?